Hello everyone, myself Rajtita Datta from National Institute of Technology Karnataka Surathkal, a third year BTech student from Metallurgical and Material Science Department. I am glad to be a part of this program and to do the project titled Reduction of Sticky Scale and Rolled in Scale in Hot Rolled Coil Surface. Moving ahead, the very first point, what exactly is hot rolling? Hot rolling is the process that involves the rolling of steel at very high temperatures. The high temperatures are usually above the recrystallization temperature of the steel, uh, but it depends on steel grade or the application which they are used in. Mostly they are above the recrystallization temperature. The purpose is to allow the steel to be easily shaped, and it is to create shapes of desired geometrical dimensions and the material property that we required, but keeping in the width constant. It tends to have scaly finish. The metallurgical processes that are involved in the process of hot rolling in the mill is, first of all, there will be a reheating, which is taking the material to the austenitic, the steel to the austenitic temperature. After that, we will be having roughing and finishing. All the mill process will be there, which will basically lead to recrystallization grain growth. And then we have run out table cooling, where we tend to see the phase transformation. If there's a very fast cooling, maybe we can see martensite. If there is a slow cooling, we will be seeing perlite. And after the cooling process, we have the coiling process. That function is basically for the structure property relation. When the width is kept constant and is rolled, the thickness is brought down, so automatically the length will be huge. So it's usually coiled and kept. Moving ahead, we here we are presenting like the process that involves in the hot rolling. First we have the molten metal, then we have a slab of a particular thickness, length and width. Those slabs are kept into the rolling mills and keeping the width constant. The thickness is usually brought down, then they are coiled and kept, and then we have huge industries and workplaces where it is used for. We'll be looking in the next slide. Advantages of hot rolling can includes that the steel material that time is malleable and then can be turned into various shapes. Enhances materials ductility, hardness, also leads to improvement of the toughness and strength of the material. It has a greater resistance to vibrations and shocks. The major sectors and applications where hot rolling steel products are used are railroad tracks and sheet metals. In automotive structural parts, we can use it, gas cylinders and saws. In their products they're used, and also it has been used in agriculture equipment and metal buildings. Then we come to the basic question, what are scales? So scales are product of oxidation that takes place during the hot rolling process. Those oxide layer develops at the steel surface, and they are not unavoidable. Like, it is a phenomena that gets into the process whenever rolling is going on. Those surface, like the oxide surface, comes. So they not only decrease the yield of the steel but also affects the surface layer. So scales are not beneficial for this steel. Just have a broader idea about the steel. We have the scales. We have different layers of scale that forms, like the different oxide layers that forms. The innermost layer is usually woostite, followed by magnetite, and followed by hematite. The inner layer has a composition of FeO, and that is the thickest part that includes 95% of the scale. Followed by it, we have magnetite, that is Fe3O4, that includes like 4% of the scale. And then followed by it, we have the hematite layer, that is Fe2O3, that involves 1% of the scale. Here we can see a picture where I have shown this mark and there's this rolled in scale. This is a type of a rolled in, how a rolled in scale looks like. Then the major classification that goes around of scales for our primary scales, secondary scales, tertiary scales, quaternary scales. Their classifications of primary scale can develop when it's having more than 1150 degrees centigrade for long hours. Secondary scale we have 1000 to 1150 degrees for minutes. Tertiary scale 500 to 1000 degrees for seconds. For quaternary scales we have 50 to 60 degree centigrade for hours. It might also be days. And then we have a XRD diffraction result of a secondary oxide. I have taken it from literature, where we can see in the secondary oxide clearly all the three phases FeO, Fe2O3 and Fe3O4, all the phases are analyzed and we receive all of them. And there's also a graph over here which shows us the approximate percentage of the oxide content versus the temperature. Here we can see a pattern is like as the temperature increases, the magnetite contents will decrease. As temperature increases, the boosted content increases, then comes to a flat line. And between 800 to 1100 degrees, the hematite remains constant. Moving ahead to common rolled in scales. So this project was basically to find out how to reduce these rolled in scales and sticky scales. We have commonly three rolled in scales, both scales, high temperature scales and sticky scales. Sticky scale is also a part of rolled in scales. So let's see each of them, what these are and how can we move ahead to reduce these scales. Both scales is a type of a secondary scale which is brown in color and is boat-like in shape, mostly located at the tail end of the coil. We have high temperature scales. Those scales are observed in a wavy-like fashion. They can be like W or M in the surface of the steel and are located at position with high transfer bar temperature across the width of the coil entering the finishing knee. After that, we have sticky scales. Sticky scales are also a type of secondary scales. They are usually black in color. They can have any shape and are located at position with low temperature in coil. One thing to mention is pickling is a process where we go ahead to remove the scales. For both scales, it can end up having pits in the scale place of the scale. But in case of sticky scale, it doesn't end up into a pit, but there is a color gradient between the surface of the steel and that of the scale. Here we are seeing a hydraulic descaler, how scales are usually removed from the surface. And then coming to one of the rolled scales that are both scales, we'll mention first the reasons that leads to the formation of the both scales. So poor nozzle condition or impression can is one of the major reasons. Low roughing mill exit temperature is also one of the reasons for both scales. If the loose scales are trapped in the inner wrap of the transfer bar, unflatness of the transfer bar. Steps which we can take to reduce these formations are proper nozzle checking. Every time we have to keep a nozzle on check and impression should be done regularly. And then we should maintain roughing mill exit temperature more than 1040 degrees C, which will be preventing the stickiness. Otherwise, it gets hard to descale the scales. In case of loose scales that are trapped, we can do is like cross section sprays and then wipe out the embedded ones. And of course, frequent check on the worn out rolls. Like descalers should always be on frequent check. And then unflatness of the transfer bar is a reason for which we can go ahead and use a leveler to flatten the surface. That's pretty much how to reduce both scales. Moving ahead to high temperature scales. High roughing mill exit temperature is one of the reasons why this sort of scales we observe. Then the slab retention time, the more the time it is the slab is on retention, the harder the scale becomes. And then not having a proper scheduling of the rules in the finishing mill. So what we can do is, the solution that we can take up is to maintain the roughing mill exit temperature below 1090 degrees C to prevent those high temperature scales. The retention time of the slab to be brought down to 2.5 to 3.5. The more retention time will lead to more higher scale thickness. And critical grade coils shouldn't be scheduled after harder grades. That should also be, that sort of a scheduling should be kept in mind, so we can avoid high temperature scales. Now going ahead to sticky scales, what are the major reasons that leads to formation of sticky scale are low furnace oxygen and high retention time if it's like more than 4 hours. Low roughing mill exit temperature can also be one of the reason. Sticky scale is a secondary scale, and secondary scales usually develops due to the poor descaling method, improper descaling, failure of descaling. All this can lead to sticky scales, and of course nozzle clogging is a major reason which can lead to sticky scale. What steps we can take to avoid the formation of these scales are to maintain the oxidizing temperature in the furnace, make it more than 2% like the oxygen content, and then the retention time should be ideally around 2.5 to 3.5 hours. Transfer bar should be used at a lower speed to have a more impact on it. The roughing mill exit temperature, try to maintain it at more than 1040 degrees C to prevent the stickiness. Otherwise, it gets difficult to descale. Descaling with a reduced transfer bar speed, again, I have mentioned it. And if you do the reduced scale, the impact for descaling will be higher. And then there should be a maintain high descaling pressure, like more than 180 bars. That can also be a prevention, like a reduction method for sticky scale. And one of the most important point, it's like the closing, the nozzle clogging. We should take that into account and check properly time to time the nozzles are not clogged, the descaling is done properly. If we keep in mind all these points and try to gradually improve them, we can end up to the reduction of sticky scales or rolled in scales in hot roll mills. Thank you for your patient listening.